Hello and welcome to the second lecture on MR spectroscopy. My name is Ivan Kirov and I'm the instructor for this mini series of classes on MRS within Enigma-U. The first lecture was on concepts of MRS. Today I will talk about data acquisition. I will show you the steps that you need to take to acquire MRS data at the MRI scanner. I'm going to go ahead and share the screen. There is also a third lecture on data processing. But both today's lecture and the lecture on data processing make good use of these two terms, which I want to start with. These are two key terms in MRS, which I would like to define first. Signal to noise ratio, or SNR, is a key concept not just in MRS, but for any MRI modality. Here is the definition for MRS. If you take a look at the spectrum at the bottom, the signal is defined as the peak amplitude or the peak height. And the noise is measured at a region where you don't have any metabolites, where you only have noise. In that region of the spectrum, you take the standard deviation of those squiggly lines there, and that's what you put in the denominator of the ratio. The signal goes in the numerator, and this is your SNR. Obviously, the higher the signal, the higher the SNR, and that's what we want to see. We want to see high SNR peaks. Each peak has its own SNR. Another desirable characteristic of an MRS spectrum is narrow line width. Line width is the peak width when measured at the middle of the peak. The technical term for this is full width at half maximum. We want narrow line widths because the peaks are better defined this way. They do not overlap. That means it's easier to measure their areas. That means the quantification is better. Okay. Now let's go on to talking about the two types of MRIs that you're likely to encounter: single voxel and multivoxel. Starting with single voxel MRS. It's readily available in most scanners. It's relatively simple to use. The results are available in real time. Right after the experiment is done, you can take a look at the spectrum. The radiologist can see it immediately. There's also high SNR, which is very important, as I just spoke. The SNR is high because the voxel is large. Because the voxel is large, there's a lot of tissue inside it. The more tissue, the more metabolites there are. The more metabolites there are, the higher the signal. This is where the highest SNR comes from in single voxel spectroscopy. One disadvantage is the fact that the voxel is so large and it may contain a lot of tissue. Gray matter tissue, white matter tissue, a mix of them, different gray matter tissue, different white matter tracts. It can also contain no brain tissue, but just brain liquid, the cerebrospinal fluid or CSF. CSF has no metabolite. So one single voxel can contain a mixture of all these compartments, and you only get one spectrum from it. So you cannot differentiate anything within that voxel. And also the other obvious disadvantage is that you only get this one spectrum from the entire brain. Of course, you can acquire multiple single voxels, but there is a limit as to how many you will be able to get within one MRI session. Okay. So in summary, for single voxel MRS, it's straightforward to implement, but it provides somewhat limited information. Okay, what about multi-voxel spectroscopy? Now, here we have a voxel grid in each of these squares. Each of these squares is a voxel. For each of these voxels, you get a spectrum. So you actually have metabolic maps with a spatial resolution of about 1 to 2 cubic centimeters. This is the volume of each voxel. These voxel grids can cover quite a bit of the brain. They can be two-dimensional, meaning one slice, or they can be three-dimensional, multiple slices. In this way, they can cover from 10 to 80% of the brain. An advantage is that in those small voxels, the metabolic line widths are quite narrow. And I spoke how this is desirable. Also, you don't need to know where you to put your single voxel. You can acquire multi-voxel data and go back to look at different regions depending on your hypothesis, which may change over time. The disadvantages of multi-voxel spectroscopy is that it's harder to do because it requires post-processing, which is lengthy, complex, and more prone to errors. Also, because these voxels are much smaller, they have low signal, low SNR. Okay. So in summary, for multivoxel MRS, it's harder to perform well, but it could be more versatile and informative. Okay, so we're ready to go at the MR scanner and acquire some data. And here are the steps for doing so. The first one is to run a regular MRI sequence to look at the brain with conventional MRI sequence such as MPRH, which is a 3D sequence used to look at brain anatomy. Then, knowing where the anatomy is, knowing where the brain is in space, we can place our spectroscopic volume. Here is an example. You see the sagittal view of the brain both in the single voxel and the multivoxel example. You can see the placements of single and multivoxel volumes. These placements are made using anatomical landmarks. For example, here in the single voxel MRS picture, the voxel is placed on the hippocampus. So within subjects, it's very important to place the voxel at the exact same place to ensure consistent placement, to ensure that you're getting signal from the exact same place from every subject. Also, the volume needs to be placed such that the edges of the box do not overlap with the skull lipids. I spoke about this in the first lecture. This is so that the lipids can be avoided. We don't want lipids to contaminate. We don't want subcutaneous lipids to contaminate our signal. Okay. But there are instances when the volume can extend beyond the brain. And that is when lipid signal is suppressed by other means. There are specific sequences specific MRS sequences that do that, and that you don't need to worry about placing the volume only inside the brain. There are also these outer volume saturation bands, which may be placed to eliminate lipid signal. See an example of those bands in both panels below. For single voxel MRS, you see the box extends on the lipids, but these bands are placed to suppress their signal. You also see an OVS band in the multivoxel MRS example shown here. This, by the way, is a snapshot of the scanner from scanning a real subject with the multivoxel MRS volume placed on the brain. See the voxel grid there. We'll take a look at this picture again in a moment. But first, it's time to do shimming. Shimming is the process of making the main magnetic field, known as B0, this is the magnetic field on the MRI machine, as homogeneous as possible. This can be done automatically or manually. It's also it may be most desirable to first do automatic shimming and then manual shimming to ensure that you make the magnetic field as homogeneous as possible, because this is very critical for MRS experiments. The more homogeneous the magnetic field is, the narrower the metabolic line widths are. So again, something that we want to achieve. And shimming is central to getting these narrow line widths. This is a snapshot of the manual shimming at the scanner. You have a real-time view of the water line width, which correlates with the metabolic line width. So you want to make the water line width as narrower as possible by manipulating the currents of coils, which are called the shim coils, which change the current so that the main magnetic field can become as homogeneous as possible, the same everywhere. Okay, once you're satisfied that your shimming is the best that you can get it to, it's time to run the sequence. Okay, Each sequence has different parameters. There are no two sequences will be exactly the same, most likely. And the parameters are tailored to the goal of the experiment that you're going to do. So the type of sequence it will be different. There's advantages, disadvantages of each of these sequences, which I'm not going to go into. But once you choose one of those, there is more parameters to choose. And I'm concentrating here on 4 main ones: voxel size, echo time, repetition time, and number of averages. And here, this is the snapshot again, showing you that these parameters, where these parameters are shown for this particular sequence, you can manipulate them here before you run the sequence. Okay, so let's take a look at what these mean. The voxel size you already know about. In single voxel MRS, it's between 2 or 3 to 8 or even more cubic centimeters. For multi-voxel MRS, of course, it's much smaller, so you can fit many voxels within your voxel grid. Here is, because this is an example of multi-voxel MRS, each of these squares is very small. So it's usually less than 2 cubic centimeters, often under 1 cubic centimeters for the voxel size. Next is the echo time, or the TE. What you need to know is that the shorter your TE, for example, under 40 milliseconds, the more signal you will acquire and the more metabolites you are likely to see on your spectrum. And here is an example of that. At the very bottom, you see the shortest TE. At the very top, you see data acquired at, or simulated. I'm not sure if this is real data or simulated data, but in any case, let's say it's acquired at long T. So you will notice that there is more peaks at the shortest TE, and the amount of peaks diminishes as you increase the TE. That's because you just get less signal, and some peaks are just disappear, and also for other reasons that I'm not going to go over now. But also, so the signal overall of the peaks that do remain is also low. So most MRS acquisitions use short TEs to get high signal and a lot of peaks. However, for some instances, long TE is preferred. What about repetition time, or TR? Most often is between 1 and 3 seconds. A longer TR will give you more precise quantitation, but it will also make the experiment longer. So there is a trade-off there. Most MRS experiments use between 1.5 and 2 seconds for TR, I would say. The final parameter of a sequence that I will go over is the number of averages. What is this? Sounds kind of strange. Well, average is the number of times the spectra are acquired in your experiment. So we have one person sitting in a mirror. You're not acquiring one spectra for very long. You're actually acquiring the spectra multiple times. For example, 256 times. And here you see on top, every squiggly line on top is one acquisition, one average. This is the NAA peak zoomed in for you to appreciate that there's many different acquisitions that make it up. And the final spectrum is actually an average of all this. So you acquire many times. The more you acquire, the more signal you get. But similar to the TR, that also comes with a time penalty because you cannot keep the subject in the scanner for too long. So there's also a limit as to how many averages you can obtain in a reasonable amount of time. Okay. Here is an example of how more averages will give you more signal. Take a look at the spectrum at the bottom. This spectrum this is just one acquisition. It gives you the worst SNR. Compare that to the spectrum at the very top. This is an average of 64 acquisitions. As you can see, the SNR is much better, the SNR for each peaks. So the more averages, the better the SNR. All right, you've run the sequence with the parameters that you have determined to be optimal for your experiment. And by the way, these parameters do not change within your study. So you would use the same MRS sequence with the same parameters for each subject in your study. Okay. The last step is the easiest. You just save the data for further processing, which would be the subject of my next lecture.